prevent a main on one substation from tripping under a ground fault on another substation, even though all the grounds are connected to the same ground mat, you can use directional ground fault protection. Directional ground fault protection is a type of protective relaying that can distinguish between ground faults on its own substation and ground faults on other substations. This is accomplished by measuring the direction of the ground fault current. If the ground fault current is flowing into the substation, then it's likely that the fault is in the substation itself. However, if the ground fault current is flowing out of the substation, then it's likely that the fault is on another substation. Directional ground fault protection can be implemented using a variety of different types of relays, including overcurrent relays, differential relays, and ground fault relays. The specific type of relay that is used will depend on the specific application. Once the directional ground fault protection has been installed, it will trip the main circuit breaker on the substation if a ground fault is detected on that substation. However, it will not trip the main circuit breaker if a ground fault is detected on another substation. This is because the directional ground fault protection will only trip the main circuit breaker if the ground fault current is flowing into the substation. If the ground fault current is flowing out of the substation, then the directional ground fault protection will not trip the main circuit breaker. Consider this scenario. If a fault occurs on substation number 2, the directional ground fault protection on substation number 1 will not trip the main circuit breaker on substation number 1 because the ground fault current will be flowing out of substation number 1. This occurs because all of the grounds are connected to the same ground mat, so the ground fault current will flow from substation number 2 through the ground mat and back to substation number 1. The directional ground fault protection on substation number 1 will detect that the ground fault current is flowing out of the substation, and it will not trip the main circuit breaker. As a result, substation number 1 will remain in service even though there is a ground fault on substation number 2. In addition to directional ground fault protection, there are several other measures that can be taken to prevent a main on one substation from tripping under a ground fault on another substation. Firstly, using separate ground mats for each substation is a good approach. Secondly, installing ground fault neutralizers can also help. Thirdly, using isolated ground sensors is another preventative measure. The specific measures that are taken will depend on the specific application. Here's a deeper dive into each of these methods. Directional ground fault protection relies on specialized relays that can determine the direction of ground fault current flow. These relays typically use a combination of current and voltage measurements to ascertain the direction. The relays are configured to trip the local breaker only when the fault current flows into the substation, indicating an internal fault. When a fault occurs on another substation, the current flows out of the protected substation and the relay restrains from tripping. Overcurrent relays respond to excessive current flow. In a ground fault scenario, a dedicated ground fault overcurrent relay is used. These relays are highly sensitive to low-level ground fault currents and are typically set to trip faster than other overcurrent relays. Differential relays operate based on the difference in current entering and leaving a protected zone. In a substation, differential protection can be applied to the transformer or bus. For ground fault protection, the differential relay compares the neutral current entering the transformer or bus with the sum of the phase currents. Under normal conditions, these currents are balanced. However, during a ground fault, a significant difference arises, causing the relay to trip. Ground fault relays are specifically designed to detect ground faults. They are highly sensitive and can detect even small ground fault currents. These relays can be used as standalone protection or in conjunction with other protection schemes. Using separate ground mats for each substation effectively isolates the ground systems. This prevents ground fault current from one substation from flowing through the ground mat of another substation. By minimizing the interconnectedness of ground paths, the likelihood of sympathetic tripping is reduced. Ground fault neutralizers, also known as ground fault resistors, are used to limit the magnitude of ground fault current. When a ground fault occurs, the neutralizer introduces impedance into the ground circuit, reducing the fault current. This lower fault current reduces the voltage drop across the ground mat, minimizing the risk of tripping breakers in other substations. Isolated ground sensors are used to detect ground faults in specific equipment or circuits. These sensors are typically installed in the equipment's ground conductor and are designed to trip a local breaker when a ground fault is detected. By isolating the fault, the impact on other substations is minimized. When selecting a protection scheme, several factors must be considered, including the size and configuration of the substations, the available fault current, and the sensitivity and speed of the protection devices. A coordination study is essential to ensure that the protection devices are properly coordinated. This study involves analyzing the fault currents of various points in the system and setting the protection devices so that they trip selectively, isolating the fault while minimizing the impact on the rest of the system. Regular testing and maintenance of the protection system are crucial to ensure its reliability. This includes testing the relays, breakers, and other protection devices to verify that they are functioning correctly. It also includes inspecting the ground system to ensure that it is properly connected and maintained. The selection of ground fault protection methods for multiple substations with a shared ground map requires careful consideration of several factors. Firstly, the system grounding configuration needs to be assessed. Secondly, the sensitivity and speed of the protection devices are considered. Thirdly, coordination with other protection schemes is required. Fourthly, the available fault current levels must be analyzed. Fifthly, the potential for sympathetic tripping is considered. Lastly, the overall system reliability requirements must be addressed. Directional ground fault protection is a widely used and effective method for preventing sympathetic tripping in substations with a shared ground map. By selectively tripping breakers based on the direction of fault current flow, this scheme minimizes the impact of ground faults on other substations. In addition to directional protection, other measures such as separate ground mats, ground fault neutralizers, and isolated ground sensors can further enhance system reliability. A well-designed and properly coordinated protection system is essential for ensuring the safe and reliable operation of electrical power systems. Regular testing and maintenance are crucial for maintaining the integrity of the protection system and preventing nuisance tripping. By carefully considering the factors outlined above and implementing appropriate protection measures, engineers can minimize the risk of sympathetic tripping and ensure the continued operation of critical electrical infrastructure. The principles of ground fault protection extend beyond substations to a wide range of electrical systems, including industrial plants, commercial buildings, and residential installations. In these applications, ground fault circuit interrupters, abbreviated as GFCIs, are commonly used to protect personnel from electrical shock. GFCIs are designed to detect ground faults and quickly interrupt the circuit, preventing dangerous currents from flowing through the body. These devices are typically installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. In industrial settings, ground fault protection is essential for preventing equipment damage and ensuring worker safety. Ground fault relays are used to protect motors, generators, and other critical equipment from ground faults. These relays are typically coordinated with other protection devices to provide a comprehensive protection scheme. In commercial buildings, ground fault protection is required by electrical codes to protect occupants from electrical hazards. Ground fault circuit breakers are used to protect circuits that supply power to lighting, receptacles, and other equipment. The effectiveness of ground fault protection depends on proper installation and maintenance. Grounding conductors must be properly sized and connected to ensure that ground fault currents can flow back to the source. Protection devices must be tested regularly to verify that they are functioning correctly. In addition to technical considerations, safety training is essential for ensuring that workers are aware of the hazards of ground faults and the proper procedures for working with electrical equipment. Workers should be trained to recognize the signs of a ground fault, such as sparking, smoking, or unusual odors. They should also be trained to use personal protective equipment, such as rubber gloves and insulated tools, when working with electrical equipment. Ground fault protection is a critical aspect of electrical safety. By understanding the principles of ground fault protection and implementing appropriate protection measures, engineers and technicians can help to prevent electrical shock, equipment damage, and fires. The design and implementation of ground fault protection systems often involve a detailed analysis of the electrical system, including the source impedance, fault current levels, and coordination of protective devices. This analysis is typically performed using specialized software tools that can simulate fault conditions and predict the performance of the protection system. The selection of ground fault protection devices should be based on the specific requirements of the application, including the voltage level, fault current levels, and environmental conditions. It is important to select devices that are rated for the intended use and that have been tested and certified by a recognized testing laboratory. The installation of ground fault protection devices should be performed by qualified electricians who are familiar with the applicable electrical codes and standards. The devices should be installed in accordance with the manufacturer's instructions and should be properly tested after installation. Regular maintenance of ground fault protection systems is essential to ensure their continued reliability. This maintenance should include visual inspections, electrical testing, and calibration of protective devices. Any defects or malfunctions should be corrected promptly to prevent potential hazards. In addition to the technical aspects of ground fault protection, it is also important to consider the human factors involved. Workers should be trained to recognize the signs of a ground fault and to take appropriate action to prevent injury or damage. Safety procedures should be in place to ensure that electrical equipment is energized before any work is performed. Ground fault protection is an evolving field, with new technologies and techniques being developed to improve the safety and reliability of electrical systems. Researchers are constantly working to develop more sensitive and reliable ground fault detection devices, as well as more effective methods for coordinating protection systems. The use of advanced technologies such as digital relays and communication networks is enabling the development of more sophisticated ground fault protection systems that can provide enhanced monitoring and control capabilities. These systems can provide real-time information about the status of the electrical system, allowing operators to quickly identify and respond to potential problems. Ground fault protection is an essential element of modern electrical systems. By implementing appropriate protection measures and following safe work practices, it is possible to minimize the risk of electrical shock, equipment damage, and fires. Continuous improvement in ground fault protection technologies and techniques is essential for ensuring the safety and reliability of electrical systems for years to come. The integration of smart grid technologies is also influencing the development of ground fault protection systems. Smart grids utilize advanced sensors, communication networks, and control algorithms to improve the efficiency and reliability of electrical power systems. These technologies can be used to enhance ground fault detection and protection by providing real-time information about the state of the electrical system and enabling more sophisticated control strategies. For example, smart grid technologies can be used to detect ground faults more quickly and accurately, allowing for faster tripping of protective devices and minimizing the impact on the rest of the system. They can also be used to coordinate the operation of multiple protection devices, ensuring that the fault is isolated in the most efficient and effective manner. The implementation of smart grid technologies for ground fault protection requires careful consideration of several factors, including the communication infrastructure, data security, and system integration. It is important to ensure that the communication network is reliable and secure, and that the data collected from the sensors is accurate and timely. The system integration should be seamless, allowing for the easy exchange of information between the various components of the electrical system. In addition to smart grid technologies, there are also several other emerging technologies that are being used to improve ground fault protection. These include arc flash detection systems, which can detect the presence of an arc flash and quickly trip the circuit breaker, and solid-state relays, which offer faster switching speeds and improved reliability compared to traditional electromechanical relays. The selection of the appropriate ground fault protection technology will depend on the specific application and the requirements of the electrical system. It is important to consult with qualified electrical engineers and technicians to determine the best solution for a given situation. The ongoing development of new technologies and techniques is helping to improve the safety and reliability of electrical systems around the world. By staying informed about the latest advancements in ground fault protection, engineers and technicians can help to ensure that electrical systems are safe and efficient. Ground fault protection is not just a technical issue, it is also a legal and ethical responsibility. Electrical codes and standards require that ground fault protection be implemented in certain applications to protect people and property from electrical hazards. Engineers and technicians have a professional responsibility to ensure that electrical systems are designed, installed, and maintained in accordance with these codes and standards. Failure to do so can result in serious consequences, including injury, death, and property damage. In addition to the legal and ethical considerations, there are also economic benefits to implementing effective ground fault protection. By preventing electrical faults and equipment damage, ground fault protection can help to reduce downtime, lower maintenance costs, and improve the overall efficiency of electrical systems. These benefits can be significant, especially for large industrial facilities and commercial buildings. Ground fault protection is a complex and multifaceted topic that requires a thorough understanding of electrical principles, protection technologies, and safety standards. By investing in education and training, engineers and technicians can develop the skills and knowledge necessary to design, install, and maintain effective ground fault protection systems. The ongoing pursuit of knowledge and innovation is essential for ensuring the safety and reliability of electrical systems for generations to come. The importance of grounding in electrical systems cannot be overstated. A properly designed and installed grounding system provides a low impedance path for fault currents to flow back to the source, allowing protective devices to quickly clear the fault. The grounding system also helps to stabilize the voltage of the electrical system and to minimize the risk of electrical shock. There are several different types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. The choice of grounding system will depend on the specific application and the requirements of the electrical system. Solid grounding provides the lowest impedance path for fault currents, but it can also result in high fault currents that can damage equipment. Resistance grounding limits the magnitude of fault currents, but it can also make it more difficult to detect ground faults. Impedance grounding provides a compromise between solid grounding and resistance grounding. The design of a grounding system should be based on a thorough analysis of the electrical system, including the source impedance, fault current levels, and the sensitivity of the protective devices. It is important to ensure that the grounding system is properly bonded to all metal enclosures and equipment to provide a continuous low impedance path for fault currents. Regular inspection and testing of the grounding system are essential to ensure its continued reliability. This includes checking the connections to ensure that they are tight and corrosion-free, and measuring the impedance of the grounding system to ensure that it is within acceptable limits. Grounding is a critical aspect of electrical safety, and it is essential to ensure that grounding systems are properly designed, installed, and maintained.